So in this video, we'll be estimating the zeros, turning points, and increasing and decreasing regions of a function. Now, before we can start identifying all of these key points in our function, we have a couple of vocab terms we need to cover. The first vocab term we need to cover is turning points. And a turning point on a graph of a polynomial function occurs when the polynomial changes between increasing and decreasing regions. So when I'm talking about a turning point, what I'm talking about is the fact that the graph is going up and the graph is going up, the graph is going up, and then it hits this point right here, and all of a sudden the graph is going down, the graph is going down, the graph is going down. So remember that graphs are always read from left to right, and if we have this point where all of a sudden the graph turns from increasing to decreasing, that is called a turning point. Now, each of these turning points will either be a local minimum or a local maximum. And so by definition, the local maximum is when the point is higher than all of the other nearby points. So, for example, if we look at that point that I just kind of focused on here, you'll notice that this point right here is higher than all of the other points around it. You can see that all of the other points are lower. This point right here is called a local maximum because all of the other points that are around it are beneath it. It may not be the highest point on the graph because we can see that this continues on forever here, but locally in this region right here, it is a maximum point. Then we can also look for local minimums, which is essentially the same thing, but it's when when the point is lower than all of its other nearby points. So if we take a look over here at this point that I just highlighted in green, you'll notice that this point is lower than all of the points around it. And if we look locally, so just looking inside of that box, what we notice is that this particular point is lower than all of the other points around it. It may not be the lowest point on the graph, because this graph does continue down forever here, so it's not the lowest point ever, but locally, in relation to the points around it on the graph, it is a minimum point. So those are some key vocab terms that we need to be aware of. The other thing that we need to be aware of is that the graph of every polynomial with degree n. So remember, degree n means that n is the highest power. So for example, say we had something like 3x cubed plus 2x squared plus 4x plus 5. So this is degree 3, right? Because the highest power is 3. So it says that every graph of a polynomial with degree n, so n is some number that we have to determine from looking at the polynomial, has at most n minus 1 turning points. So what we can conclude about this example function that I just added right here is that because this example here is degree 3, we expect to see at most 3 minus 1 or 2 turning points at most. So just a couple of key details to know before we start diving in and identifying zeros, turning points, and increasing and decreasing regions. Now for this example, all we're going to do is we're going to estimate different turning points and zeros, and then we're going to describe the increasing and decreasing regions. So while some of these we may have to kind of estimate ourselves, so they may not be identically perfect to the graph, we're going to do our best. So we're going to start with finding the zeros. And remember that zero is a fancy way of saying the x-intercepts of the graph. So we're going to start by finding the x-intercepts of this graph. So I'm going to find my zeros, which again are x-intercepts, and I'm going to go to my graph and find them. So here I can see I have a 0 at the point -2, 0. I can see I have a 0 at the point 0, 0. I can see I have a 0 at the point 1, 0. And I can see I have a 0 at the point 3, 0. So I can visually pull those straight off the graph just by looking at where we cross the x-intercept. And remember that these zeros are found if we were to set f of x equal to 0. So we could factor this, we could solve this using synthetic division, we could solve it all of those ways, but because we have the graph, we can clearly see these zeros straight on the graph. So the next thing we're going to find are the turning points. Now, remember what we talked about on the last slide with turning points is that the maximum number of turning points that we can have is n, which is the degree, minus 1. So here we can see the highest power here is 4. So we have 4 minus 1, which means there's going to be 3 turning points maximum. So I'm going to look for areas on the graph where the graph changes from increasing to decreasing. And as I do this, I'm going to kind of highlight my increasing and decreasing regions too. So here I notice to start, because remember I read graphs left to right, that the graph is going down, the graph is going down, the graph is going down, the graph is going down. And then all of a sudden I reach this point here where the graph flips around and is now going to start going in another direction. So now I hit this point in blue, the graph is going up, the graph is going up, the graph is going up, and then here it switches to be going down. And so every time I switch directions here, as I'm reading this graph from left to right, I'm writing all of my green regions are my decreasing regions, the blue points are my turning points, and then my purple regions are my increasing regions. So you can kind of see where my different regions are. So we see here that we have 3 turning points. Now, unfortunately, these are not at super nice points. So what we're going to have to do is we're going to have to just estimate what these coordinates are. Now, I'm going to estimate as well as I can, knowing that they are not going to be perfect. So when I look at this point here, if I kind of go up to the x-axis, I notice it's hitting at about -2.4. This doesn't have to be perfect. It's just an estimate of where this turning point is. And then I can see that my y-coordinate is at -9. So that's going to be my first turning point. So I'm going to record that here, comma, -9. Now, I also want to make a note of if this is a local minimum or a local maximum point. And when I look here, what I notice is that this point is lower than all of the other points around it. So because of that, this point is a local minimum. Now, if I move on to the second point here, again, I'm just going to estimate. I can see that x is about 0.5 and that the y value is about 1.5. So I'm going to record that over here in my list of points. So 0.5, comma 1.5. And that is a local maximum point because all of the other points around it are lower than that particular point. It's the highest point in its local region. And then finally, we take a look at this third turning point, which if I again just kind of estimate here, I can put at about x is 2.3 and y is -9. And so again, I'm just going to record that estimated point, and then I note that this point is lower than all of the other points around it, so it is a local minimum point. Now, the last thing I need to do here is I need to identify my increasing and my decreasing regions. So I'm going to start with my decreasing regions, just because the graph starts off decreasing. And what I notice when I take a look at this graph is that this decreasing region right here occurs for all of the x values that are smaller than -2.4. So this all happens before -2.4. So I can represent that region by saying all of the x values that are less than -2.4 result in a decreasing area of the graph. However, this isn't the only decreasing area of the graph. We have an additional decreasing area right here between x is 0.5 and x is 2.3. So what I'm going to do here is I'm going to put x in the middle, And I'm going to say the graph is also decreasing when it is bigger. The x values are bigger than 0.5, and they are less than 2.3. So notice here that it starts at 0.5 and then it stops decreasing at 2.3. And then finally, we need to find our increasing regions. And if we do that, we can see we start here when x is 2.4 or negative 2.4, and we go up to when x is 0.5. So it's kind of the opposite of that last one there. So we're going to have x in the middle, and it's when it is larger than negative 2.4 and goes up to 0.5. And then we can see that it starts again at 2.3 and goes for all eternity. So all of those x values that are greater than 2.3. So let's take a look at one last example here. So let's go ahead and start by finding and estimating the zeros of this particular graph. So remember, zeros, we're looking at where the graph crosses the x-intercept, and while these don't appear to be super nice points, they appear to at least be, like a 0.5 type of thing. So our zeros here are negative 2.5 comma 0, negative 1.5 comma 0, and then a positive 1.5 comma 0. So while they're not super nice points, we do at least have points that are like a 0.5 or appear to be that way. Now, the next thing we need to find are our turning points. And so I'm kind of going to find my turning points and my increasing and decreasing regions together. So let's find our turning points as we do increasing and decreasing. So remember that we're always going to start on the left-hand side of the graph. Here in purple is where the graph is increasing. And then we hit a turning point here just shy of that point of negative 2, 1. So I'm going to estimate that this point is negative 2.1 for x and a positive 1.9 for y. It doesn't have to be perfect. Again, remember, these are just estimates, but that's kind of what I'm estimating by looking at the graph. Now, because this point is higher than all of the points locally around it, this is a local maximum point. Now from here, the graph starts to decrease, 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 and it hits a low point here at what looks like it's about, 0.3, we'll say. It doesn't need to be perfect. And x is about negative, or y is about negative 6. So again, it doesn't need to be perfect. It's just an estimate. And this point looks like it is the lowest point in its area, so we have a local minimum. And then again, the graph goes up once again. So we have two increasing regions and a decreasing region here. And so this time around, I'm going to start with my increasing regions because the graph starts off increasing. So what I notice here are that all of the x values that are smaller than negative 2.1 have an increasing region. So I'm going to say that all of the x values that are less than negative 2.1 result in the graph increasing over time. I then notice that all of the x values that are larger than 0.3, so all the ones over here, are also increasing. So we have increasing region smaller than negative 2.1 and an increasing region bigger than 0.3. We then have one decreasing region here, and it's sandwiched between two values. And I can see here that my decreasing region is sandwiched between negative 2.1 and 0.3. It's increasing or decreasing in between those 2 points. So I'm going to create a little sandwich here and say that the decreasing region occurs when x is on the bigger side of negative 2.1 and x is on the smaller side of 0.3 to kind of show x is in the middle of those 2 points.